Well, thank you very much, Dennis, for inviting me back. I'm delighted to be a part of this exciting event again after the first two successful virtual pipeline summits. The topic of this edition is right up my street, so I am really looking forward to the 5 technical presentations we have lined up over the next couple of hours. Speakers will talk for 15 minutes, and then we will have time to address questions from you, the audience. So please send those through the chat and the Q&A function at any time throughout the presentation, and we'll address them at the end. Starting the session this afternoon is Michael Smith with ROSEN Group here in the United Kingdom. Michael is a chartered chemical engineer and data scientist with a master's degree in chemical engineering from the University of Cambridge. Within ROSEN, he leads the development of new asset integrity technologies with a specific focus on integrity analytics, the use of data analytics to support integrity management decisions. Michael will present what sounds like a very 2020 topic, virtual inline inspection, condition assessment for the most challenging pipelines. There's an ever-increasing need to operate aging pipelines safely and efficiently, and pipelines that are challenging to inspect are a particular problem. Like all pipelines, we still need to understand their condition, and historically that has involved costly adaptations to inspection technology or to the asset itself. These days, however, we have the option of a virtual inline inspection using machine learning. So Michael, over to you.
All right, thank you very much, Danny. Good introduction. So yes, what I'd like to talk about is machine learning for condition prediction in pipelines as an alternative to the things that Danny just mentioned. And so why would we want to do that? Maybe it's the only option that you have left for a pipeline. It can be very expensive to modify the pipeline, or it can be very expensive to modify ILI technology. And actually a relatively simple thing that you can do, not technically simple, but practically simple, is to do some sort of machine learning based assessment. And this is becoming more and more feasible, let's say, more and more plausible to do, simply because we have so much data available within the pipeline industry. So, I mean, if you're brave enough, certainly to go and collect it all up and then structure it and put it into the format that it needs to be in for machine learning, which is quite difficult and really quite time consuming as well. So ROSEN is no different in this sense. We have lots of historical data, and we are going through this somewhat painful process of collecting it all up and trying to make it machine learning ready. And that's it. And this is in a structure that we call the integrity data warehouse. And that's got plenty of stuff in it. It's got, as you can imagine, inline inspection, pipe tallies for all sorts of different threats and technologies, design and construction information for the pipelines, simple stuff like you can see here. Lots and lots of environmental data now from open sources, and I'll talk in quite some depth about that a little bit later on. Operational data is another big one. And then I think we'll probably hear about this in a few of the presentations, but survey data always comes in handy with challenging pipelines, things like cathodic protection surveys and coating surveys. And we've been going through this process, like I say, and we believe we're about 30% complete with it, and already we're up to a little over 8,000 pipelines worth of data. So this is already more than big enough to start doing meaningful machine learning. All right. So the idea of virtual ILI then, it's an attempt to predict condition without actually putting an inspection tool within a pipeline. So if we have an uninspected pipeline, a challenging pipeline, and we have this big list, this big data warehouse with inspected pipelines, all the information for inspected pipelines in there, then that really lends itself to supervised machine learning techniques. I'm not actually going to go into a huge amount of detail about the machine learning itself, and rather just stick with the concepts. I mean, the first thing to say is that you can do this for any kind of pipeline threat, really. Anything that you can measure using ILI or equivalent, anything that's represented within your list of inspected pipelines. I'm going to focus here on corrosion, and even more specifically external corrosion, just because we've by far and away made the most progress with this, and it's also a very endemic threat as well, so it's well worth investigating. What I want to show first of all is like an early step towards this virtual ILI thing. So, I mean, the very least you could do, let's say, for a pipeline is to come up with a single value which somehow describes the condition of that pipeline. Okay, so that's what this is all about. It's like a super low resolution ILI, if you like. So to do this, what we did is we isolated those pipelines where there's a lot of metal loss inspection data, because we're looking at external corrosion, and pipelines with nice complete design and construction information. And at the time of doing it, that was about 4,500, a little over 4,500 pipelines. And they were pretty well distributed spatially. You can see there's good representation in all of the continents, North and South America, Europe, Africa, Asia Pacific, and so on. And they're pretty well distributed through time as well. I mean, they go back as far as the 1940s, so that's like an 80-year-old pipeline. Most of them are about 30, 40, 50 years old, but you do have pipelines from the last decade as well. So good distribution in terms of ages. And there's other kinds of characteristics we can look at. We can look at coating types, diameters, wall thicknesses, basic design and construction information. So back to the supervised machine learning idea. Like I say, I'm just going to go into this conceptually, just restricted by time somewhat. But what we're doing with supervised machine learning is trying to develop a function. And that function is going to map to a target variable. So I mentioned before that we want to come up with some sort of single value that we can assign to a full pipeline to represent its condition. So the target variable that we chose in this case was the anomaly density, number of external corrosion anomalies per kilometer of pipelines. But we binned that into classes based on the order of magnitude. So you can see here the low class is where you've got fewer than 1 anomalies per kilometer, and then 1 to 10 is moderate, 10 to 100 is high, and so on. So you've got these 4 classes, and that's what you're trying to predict. And you're trying to predict those with appropriately named predictor variables. That's these x values of the function. And that's all of these kind of things that I've already mentioned. Okay, so your final data set prior to doing any training, prior to starting any machine learning task at all, looks like this. You've got all of your predictor variables listed there. You've got that target variable, which is the class, and then you've got these 4,500, 4,600 rows, each one pertaining to a particular pipeline. So this is where we'd start the machine learning process. Like I say, I'm not going to go into details about the algorithm. It's essentially a decision tree algorithm, so it produces a load of if then else statements to kind of sort the data into categories. If anyone's really interested, come and talk to me afterwards in the virtual booth. I'm just going to skip straight to the results though of this first step towards virtual ILI. So what you can do, you take that data set, you siphon some of it off and you keep it in reserve, and that's going to be the test data set, and you go ahead and train the model on everything that you kept. The model gets applied to the test data set, and then you can make predictions, and then you can compare those predictions with the true values. And you record that all in a matrix that looks like this. And here are the results. So you can kind of see immediately the gray diagonal, the dark gray diagonal down the center, that's where you want everything to line up, because that's a perfect prediction. You can see immediately that it's performed reasonably well. And actually it's 58% of pipelines classified perfectly. So 58% down that central diagonal, and 92% are within 1 order of magnitude. So that's pretty good. And when I say 1 order of magnitude, I mean 1 class either side of the correct class, because the classes were split into orders of magnitude. So 92% is pretty good, certainly if we relax the performance metric a bit. Now that's, like I say, just a small step towards virtual ILI. If you were going to do this properly, well, I mean, the small step is already useful. You could use it to, say, prioritize those pipelines that you should make pickable or you really need to make pickable. But yeah, if you really want to say you're doing a virtual ILI, then it has to be a higher resolution than just 1 value for an entire pipeline, clearly. But in order to do that, we need to make the model of course, a little bit more sophisticated. And one of the motivations for that is that you have a lot of outliers in there. Well, not a lot of outliers, but enough to be concerning. So you might have spotted these before. Bottom left there, we've got 4 pipelines where the prediction is very high, but the true class is low. So that's effectively false positives. That could have some cost implications. And then you've got the opposite thing happening in the top right there. 6 pipelines with a prediction of low when the actual class is very high. So that's clearly a potential safety issue. So we want to fix that. And as I say, the best way that we can do it is to add new predictor variables to the model. And I mentioned earlier, one of the best sources of data is open source environmental data. And for external corrosion, that's really useful. So there's a few different variables here. I'm going to just quickly talk through each of them in turn. We've got land use, we've got soil properties, crossings, terrain, and climate. And all of these can be used to good effect with external corrosion prediction. Okay, so land use first of all. There's an open source land use data set. Land use is the way that the land is used. It's very appropriately named. And you can see this map. You can get these maps all over the world, essentially varying degrees of reliability. But you can separate out things like this. These are the urban areas down the left in the key, more rural areas, and sort of water-based areas. That's what we could probably call them. And what you can do, if you take a patch of land where a pipeline is located, you can plot the pipeline route through it, and then you can start to spatially align that land use data set along the pipeline. So for each pipe joint, even, it depends on the level of resolution that you've got, but you can, and maybe at each pipe joint, you can start to say what the land is used for in that vicinity. And then that is actually quite useful for corrosion prediction. So the next question would be, does that correlate? Do particular land use categories correlate with corrosion? And the answer is yes, they actually do. So you can see here high prevalence of external corrosion. That's actually the percentage of joints that have corrosion. In mine, dump and construction sites, for example, or inland wetlands, they're particularly high, whereas say permanent crops, pastures, that's much lower. So these kind of things can help out a machine learning model. If you're really keen, you can go further than that and start looking at soil types. You get some really interesting names like castanozems and podzaluvisols and all sorts of things that I don't understand. But again, they're good for prediction. So you can see that the soil types help to discriminate against areas with and without corrosion. You can see that quite clearly here. Crossings is another one. These could be roads, there could be power lines, there could be with rivers, for example. This is, of course, a map of roads. And there is some evidence within the data set that at a road crossing, you have a slightly higher prevalence of corrosion than when it's not at a road crossing. And it's a marginal trend, but when you sort of add up these marginal trends all together, it starts to become very, very useful, very powerful for prediction. A couple more just quickly. Terrain, this is an elevation map. We can look at how the anomaly density varies with the elevation. This is actually for a smaller subset of pipelines just to make the trend clearer. And you can see here that as the elevation goes up, and it's not by a huge amount in this case, you get this very steady reduction in anomaly density, so from bottom to top of this chart. And you could speculate all day long about why that's happening. Usually these things happen, it's not just the elevation itself, it's the interaction of that variable with other variables, other pipeline characteristics. Finally, climate, and one variable in particular that we've found really quite useful, really quite interesting, is precipitation. So rainfall in most parts of the world, some parts of the world, there'll be significant snowfall as well. And there's a few different trends with rainfall, but one really interesting one is the impact that it has on cathodic protection. And you can see quite clearly here a negative correlation. This is quite a strong negative correlation as these kind of things go. You can see the CP becomes more electronegative as the rainfall goes up, which is something that we kind of know, but it's just very nice to see it played out in the data, and that means you can actually start to use it for prediction as well. Okay, so to sum up then, what you can do once you've got all that extra high granularity, high resolution data is you can point at a single pipe joint or a segment, depending on the resolution. You can specify all of these parameters, and you can start to do that same classification process, low, moderate, high, very high. So you can go along the pipeline in that fashion. And then rather than just now being able to prioritize between pipelines, you can make some more sophisticated decisions. So these could now be your targets for mitigation or for in-field investigation, direct examination. So this is like it's like a next generation version of direct assessment, I would say, or at least the part of it which does the risk assessment. Okay, so that's me done. So I'm happy to take any questions. And like I say, if anyone wants any more details about it, then feel free to come and talk to me in the ROSEN booth.
Well, thank you very much, Michael. Presentation. We do have some questions coming in already. I had one, and incredibly, somebody else has asked the same one. It's Roy Surges, who says, do you think this has a chance of being accepted by regulators without actually doing an inspection? Is any work being done on the regulatory front to promote this capability?
I mean, I couldn't speak on behalf of regulators, but I would be loath to do so. It depends on a couple of things. It depends on why you are doing it. For a start, what happens if it's the last resort for a pipeline? So that's the first thing. So if it is the best option that you have, then you can't not accept it. So maybe that's the first thing. Second thing would be all about performance. So you can demonstrate the performance within a data set like I have here, and the performance is pretty good. But it's not until you start going out and digging in a pipeline where you've made the prediction that you can really see what the real world performance is like. So I guess that would be a point to get to before you could really comment on acceptance by regulators or anything like that.
Yeah, it's an interesting one. I wonder if it would ever get to the point where that becomes the norm. You know, even for piggable lines, you just go off the database.
I think there would certainly have to be some coded guidance associated with these kind of methods. More like I say, like an extension to the existing direct assessment guidance for machine learning based techniques, and maybe, yeah, you're right, Danny. Maybe that kind of thing would help to increase acceptance.
Yeah, I guess maybe a concern would be that for an unpiggable line or a challenging line is perhaps the thing that's making the pipeline unpiggable is something that could make it
unique. You're just driving a harpoon straight through the method, but that's absolutely right. It's certainly possible that that unpiggable pipelines have relatively unique characteristics in terms of corrosion, and this is the kind of thing that we need to figure out.
Mm-hmm. Do you think you could ever use that model to identify an area for repair? I guess that's one of the goals of an ILI specific.
I think so. I mean, we have done that. So I mean, you can always make the predictions. Making the predictions is kind of the easy part. Getting it right is the hard part. So you could flag areas for repair, but then if you've flagged false positives, then people aren't happy. So that's what it's about.
Well, I guess there's an element of in-field verification, which is something that somebody else mentioned. Ahmed El Arbi. I guess you take the data from the virtual ILI and then aim to verify it in field, right?
That would be the intention. Yep.
Okay, and we have another question from Gonzalo Cabrera. Can you use virtual ILI to determine level of risk for an in-service pipeline lowering as per IPI 1117?
Yeah, it just depends on how you set your target variable, I guess, how you set up your machine learning model. So, you know, rather than we've done the same kind of thing. Rather than predicting classifications, you predict probabilities. Essentially, you can set up machine learning models to do that. I mean, you could do it with this case. You could simply have the probability that say a pipe joint or a pipeline is within each category. So you can use it to predict probabilities, and that's one half of risk. The consequence side, I was thinking about this just this morning, actually, like how do you incorporate the consequence side with machine learning, and would that even be something that you would do? I'm not so sure, but you can certainly get the probability side of it, and that's one half of risk.
Yeah, nice answer. Okay, we've got a few more questions. I think we're running slightly short on time, but I think we can squeeze in a couple more. We have one from Kaveh Sadikani. Is any effort being done on image detection of corrosion, machine learning and artificial intelligence, and creating a database for visual inspection at ROSEN or the wider industry?
I'd have to ask one of my colleagues in particular what's going on there, but yes, I believe so. I believe there was some there was some research into visual inspection and the identification of anomalies in the manner described. But I don't have details of that, so I couldn't go into it.
Okay. Saeed Khanna was very impressed with your correlation of soil type with type of corrosion. So good job there.
Soil expert, fantastic.
I knew there was one. And a final question from Sachin Kolhe. How does the temperature of the service fluid affect the corrosion rate to reduce the life of pipelines?
For external corrosion, it's going to depend very well. For internal corrosion as well, it's going to depend very much on the mechanism. So, I mean, I think we'd have to. It's not necessarily the temperature itself; it's the interaction between the temperature and other things. So you could have, say, an interaction between the soil and the coating, and and that kind of thing, and the temperature. So it's kind of difficult to say outright exactly what it would be, but there certainly are external corrosion mechanisms that are temperature dependent. In this case, we didn't actually use temperature.
Right. Presumably that's another variable that you could add in.
Absolutely right. Yep.
Great. Well, thank you, Michael. Before I let you go, I just wanted to also express gratitude from Young Pipeline Professionals Europe, because you see, Michael recently ran a training session at the Virtual International Pipeline Conference, but chose to donate his trainer's fee to cover the admission fee for young pipeliners to attend the conference. So we really appreciate it, Michael. Thank you.
Very welcome, Danny. Also thanks go to Erica Santana and Danny Aronson and Daryl Banster as well. Yep.
Perfect. Thanks, Michael.